All right, so in multivariable calculus, you've probably gotten pretty good at integrating over straight lines. But what happens when the path isn't straight? Today, we're going to crack open a super powerful tool for dealing with curves, the scalar line integral. Let's dive in.
Think about it for a second. How would you actually find the mass of a wire that's all twisted and curved through space? Or maybe the area of a fence that snakes along some hilly terrain? Your standard everyday integral, the one that just works along a straight x-axis, it just can't handle these kinds of curves. We need something a bit more sophisticated.
And here it is. This is our solution. It's called the scalar line integral. It's specifically designed to add up the values of some function, we'll call it f, along pretty much any curve c you can think of. Now the real secret sauce here is that little ds at the end. It's telling us we're integrating with respect to arc length, which is just a fancy way of saying we're following the actual length of the path every twist and turn.
The best way to get a feel for this is to think of it like you're on a journey. Imagine you're hiking a trail. That trail, with all its ups and downs and bends, that's your curve, C.
Okay, so as you're walking along this trail, imagine at every single step you're measuring something. Maybe it's the temperature or the altitude at that exact spot. That measurement you're taking, that's your function, f. So going back to our first examples, f could be the density of that wire at each point, or the height of the fence right where you're standing.
So then what's the integral itself? Well, it's just the grand total of everything you measured along your entire hike. If you were measuring density, the integral gives you the total mass of the wire. If you were measuring the height of the fence, you get the total area. It's a really elegant way to think about it, right?
Let's just quickly compare this to what you already know. A standard integral adds stuff up along a totally straight line, like the x-axis. A line integral, though, lets us do that same thing, but along any wild, curved path we want, either in 2D or 3D space. That's the huge leap forward. We're breaking free from the straight and narrow, literally.
Okay, now for the good stuff. How do you actually solve one of these? Well, there's a fantastic 4-step recipe that works every time. First, you parameterize. You turn your curve C into a vector function, r of t. This is how we get it into a language algebra can understand. Second, you compute the magnitude of the derivative. That's r prime of t. This part is kind of the magic trick. This gives us that ds element, but in terms of t, which we can actually work with. Third, substitute. You just plug your parameterization into your original function, f. And finally, step 4, integrate. You solve the new, much friendlier definite integral with respect to t. Let's see how it works.
All right, enough theory. Let's get our hands dirty and put this recipe to the test with a classic example, finding the mass of a wire that's shaped like a helix.
So here's our mission. We've got the path of the wire, defined by r of t, for t between 0 and 2 pi. And we know its density at any given point is just its height, its z-coordinate. Our job is to find the total mass.
Let's go through our recipe step by step. Step 1, parameterize. Well, lucky for us, the problem already did that. So check. That was easy. Step 2, compute the magnitude of the derivative. So the derivative of r of t is just negative sine t cos t 1. Now for the magnitude, we take the square root of the sum of the squares. So that's the square root of sine squared plus cosine squared plus 1. And hey, remember our old friend, the Pythagorean identity? Sine squared plus cosine squared is just 1. So the whole thing simplifies beautifully to just the square root of 2. Awesome. On to step 3, substitute. Our density function is simply z, and if we look back at our parameterization, we can see that z is just equal to t. Easy enough. Finally, step 4, integrate. We put all the pieces together. We're going to integrate our function, which is t, times our arc length element, which is the square root of 2, all with respect to t, from 0 to 2 pi.
And when you solve that pretty simple integral, boom, there's our answer. The total mass of that whole helical wire is 2 times pi squared times the square root of 2. It looks like a really complex problem, but our recipe just tore right through it.
So let's just boil this all down. What are the big things to remember? First, scalar line integrals add up a function's values over a curve, not a boring old straight line. Second, they're not just abstract math, they model real-world things like mass and area. And, most importantly, you have that rock-solid 4-step recipe to solve them every single time.
Okay, so we've totally mastered how to add up scalar values, things like density or height, that just have a magnitude. But that leaves us with a really fascinating question, doesn't it? What if the thing we were measuring had a direction, too?
What if we wanted to calculate, say, the total work done by a wind that's pushing you along your path? Well, for that, you're going to need the other half of this story, the vector line integral.